Joining the meeting.
Hello, everybody. Switch the camera so it's just pointing at me. Yeah, all right. That's fun. There's this, and there's that, and everything. All right. Hey, we're actually getting started nearly on time. And look at all this stuff, it's still on the board.
Yeah, you just have to increment the number.
I don't even have to do anything. I am so pleased. So, I kind of realized last time we ran, and a good way to sort of start this off is to take a little break, take a little moment. We can even erase some of this equations, because although we'll be doing this again, and talk about exactly the overall architecture of this entire thing. I don't know if I even actually talked about that. And keep all this terminology there, though, because this is important. Okay, so the whole point of this is to come up with a fast way of doing hair simulation, right? And it's full-on hair simulation. So what we start off with, and so start with a groomed hair model. I'm going to draw some bad hair here. So full-on groomed hair model. And so we'll just call this the groom. Then we have going through space and time, a whole bunch of training data. And so this is head motion. So we have a whole bunch of, we've recorded a lot of head motion. We've got, or done stuff. We've animated the head. We've tried to create motions that we think are going to be done by the person driving this thing, or done by however we're going to be doing this. So that's one to start with. This is all start with groom, head motion, and this stuff goes into a full-blown simulator. And we spend some time and simulate the heck out of this hair. So it's all nice flippy hair. There's all sorts of stuff going on and exciting things. 500 frames of head motion, so we know how the head is moving. And then 500 frames or a 5,000 or 50,000, however many you want to. They were number 500. This is what we have. Then the one thing that we suck caring about so much, like I said last time, is the groom. The groom requires guide hairs and all sorts of things to basically shape the hair, but we don't really care about that after this. This has become something where it's just 100,000 hairs on a head motion, and 100,000 moving hairs on head that we're happy with. We like the way that looks. All right, so what are we going to do? We're going to build something that runs way faster. And so first of all, step one is to figure out guide hairs. We did this last time. We spent a lot of time, we went through a k-means clustering kind of thing and to try to figure out the best guide hairs that represent the motion, not the groove. We want to know how this thing moves, and what we want to do is reduce the 100,000 hairs into a representative, maybe 200 or 500 guide hairs that sort of capture the motion of the hairs. And we're going to try to find the best guide hairs. And in fact, because last time, and we're not going to talk about it that much, we're going to assume that that's done. All right, now, two. We're going to build up a relationship between the guide hairs and the normal hairs. So we've got 200 hairs that are going to be representing the motion of the head. And we want to build up this sort of, if my guide hair moves, how does my normal hair move? And so this is going to be building up linear, and it's going to, we'll go over it again just to make sure, because this is the place where we stopped. The equation, moving normal hairs if we know if the guide hair moves, the guides move. So basically, we built up something. Again, it's not the groom. It's the simulation space kind of thing that says, I've got these representative hairs. I've got my normal hairs. I know that those guys are working together. And so we're going to try to build up a really small, and this is key, a small relationship between guide hairs and the normal hairs, because there's a lot of normal hairs, and we want to make sure that we can run through this. Hairs move. We can move the normal hairs really, really, really fast. We want to do that fast. Okay, so step 3 is moving the guide hairs. Move them. There's a whole section of this paper that we're going to sort of skip over because they describe guides. That's it. They describe how they move the guide hairs, and they build up a spring system based on some work done at Stanford for animating hairs. But at the very beginning of the paragraph, of the section, they say you can use whatever simulator you want to move the guide hairs, as long as it's fast. It's a simulator, so now think about it. We have a simulator that we use to build up our system. Now we want to, maybe we use the same simulator that we used here, that we're using to move 100,000 hairs, but now we're only moving 200, just 200. So this needs to be fast and as accurate as possible. And they talk about using the Stanford system, the springs that come and go to represent the friction between the hairs and sort of the volume of the hairs. Because remember, you've got this head of hair where if you know all the hairs and you have a full-on simulation, you can actually simulate the volume and the behavior of this. Now we want a guide or a simulator that can move the guides and still look here. We're going to leave this as exercise for the reader or exercise for the software that we downloaded from the internet. We'll skip over that. But once we have that, then, because we built up this, we're going to use 2 to move everything else. Everything. All the hairs. We're not done. You think, oh, no, we're done. We got something that looks good. It may be good for a video game, but we're not done. This is the cool part, well, a cool part, is that we want to do collisions. And we want to do them fast, right? So this is the part, these steps are what we're going to go through today. We'll skip over that because we just talked about it. But at this point, there are collisions that are going to be happening. There are 2 different kinds of collisions. First of all, you're moving your guide hairs using a hair simulation, and the guide hairs are not going to collide with your geometry, right? Hopefully, if you've got a long head of hair and you're moving your head around, these guide hairs are going to stay outside of the shoulders. They're not going to bump into things. So that's not going to happen. But there's nothing to prevent that from happening with these normal hairs, right? We're going to be moving all the other hairs based on just this linear equation thing. So they may actually bump into the shoulders. How do we deal with that? Hold on. And then there are hair-to-hair collisions, which we really wouldn't want to see. We want to have hair-to-hair collisions not resolved. We want to make sure that the thing behaves like hair and stays across it. And in fact, if you watch the video, and I'm not going to bring it up, it'll take a little bit too long, they have some lovely hair-to-hair collision where one hair, so as the guy is moving his head, the little strands are traveling across the top of the hairs as you'd expect them. So there are 2 types of collisions that we're going to deal with. Geometry collisions, which should be minimal because these guide hairs aren't hitting geometry because we're not doing it perfect. And then also, well, gee whiz, hair-to-hair collision is a pain in the butt. I've used a full-on simulator to do 100,000 hairs. I've got it so that it doesn't do hair, the hairs don't collide. But this thing takes 10 minutes per frame to run. How are we going to do hair-to-hair collision in real time? Well, what we're going to do is approximate it, and we'll see how to get to it. Once we've done all this, figured out the guide hairs, we did that last time, and do all this, we have full head of hair, 100,000 hairs, moving in 30 milliseconds. Don't believe it possible? There's a YouTube video where it looks like it's happening. But we'll see if we can actually get there. All right? So far, so good. Right? Right? Everybody's sort of on board with this? All right, so we're going to erase this. And then we're going to review our terms one more time. So each hair in the system is actually represented by a series of nodes or hair particles. A certain number of hair particles associated with each hair, whether it's a guide hair or a normal hair, there are particles associated. And there are a couple of variables that are going to show up. First of all, the position of that particle in world space, and I actually should draw this over here. The particle in world space when you've simulated, when you're moving it around. S bar, particle local to the head at the origin, looking down the x-axis. It's the local space coordinate of the hair particle. And then S star, and I'm going to write this over here. You can actually have a star bar here. That's the location of the hair at its rest state. That kind of thing. And then T, this is T, that's the head transform. Remember, a particle is both a position and a tangential vector to give it an orientation. All right? And the T will take you from local hair coordinates to world coordinates. So take this times that, you get world coordinates. There's also a B. We should go over B.
Excuse me, Doug?
Yeah, go for it.
What is that local to? Are you talking about local to the previous node or to the head?
That's local to the head at the origin in looking down the x-axis. So coordinates to the head. And
it's like the coordinate without the rigid transform.
Exactly. Yeah. And you can tell because the only thing that's happened here is we've got a world space coordinate due to, and this will put it back into, this will take this, it's just a matrix transformation. So if the head's bopping around, it'll move this head so that it's at the origin pointing down the x-axis, but that, now it's still in the same spot, right? So that's S bar. That guy goes right over here, and that hair is doing that crazy whoop. It's still simulated. It's just at this coordinate system with this at the origin. And then S bar star is the rest state of the hair. That's where it is just a groove. We haven't turned on gravity, we haven't done anything, it's just the hair groove. That's where it wants to go if everything is steady. There's B, and B takes you from the rest state to the actual state. So S equals B times S star, and usually we're doing it in local coordinates, so it looks like that. Let me make sure I'm not lying. Let's just turn the page here. Did I do it right? S bar star equals S star, yes. Okay. So B is the, it looks like HB, that was a bad A. Let's go for fixing that. That's head transform. And then B is transform from rest to, oops, yeah, to the simulated or sim space. There are sim coordinates, whether it's local or world. All right. So if you took the bars off, that should still work. Yes. that should still work. But in general, we're doing it at local space because it's nice. Okay. Okay. So, step one, find guides. And we talked all about that. We're going to come back to a little bit about the stuff, but that's going to be farther down when we deal with collisions. We went through a big thing and just a quick overview of it. We took the hairs, we built up this huge graph of all the hairs and all the little nodes on the hairs, figured out when nodes or hair particles got close to other hair particles. Other hair particles, we put a node in the graph and created an edge between the two nodes that represent the particles. So the graph actually has the same number of as there are hair particles in the system. So if we have 30 hair particles per hair and 100,000 hairs, that's 3 million hair particles. That means that this graph is 3 million nodes big. And then there are edges between each one of the nodes in the graph and any of the particles that come close to the other particle during the simulation. So there's a certain number of frames. They have number of frames equals 500 in this case. So we're going to be looking at that and building up this great big graph with a whole bunch of edge connections. But you know that you're not going to have an edge connection. You're going to have an edge connection between this particle and this particle because they're close in proximity. But that particle and this particle over here, quite frankly, unless you're doing some crazy stuff, aren't going to be coming close to each other. And in fact, they prune the graph, or they shrink the graph down by removing edges of particles that don't stay close to each other for less than 20% of the frame range. So they look at this frame range and they say, you know, if particles come close to each other for a whole 100 frames, we still don't care. We want the particles that are really neighbors during this thing. So they build this big graph, and then they use a graph reduction, or clustering algorithm called K-mean, or well, K-clustering. And it breaks the graph into chunks, where the chunks are particles that have a lot of strong connections between them. And then one chunk versus another has a kind of a guarantee that the number of edges that are shared between those, and there will be edges shared between the big chunks, is going to not be that strong. It's going to try to find these natural divisions behind it. And it's a hard problem, but there are people who've written solutions for these kind of hard problems before, and they just downloaded a library from the internet. Once they've done that, okay, now once we've done that, we've basically taken our great big, let's actually draw this out just to remind me and everybody else. So we've got this thing, and we've got edges connecting all sorts of things. We've got all these edges going everywhere between these nodes. And some are strong and some are not so strong. And eventually we come and we say this group has really strong, these edges, these particles stay near each other a lot. And these guys all stay near each other a lot. But these edges in between, not so much. These guys might be near each other 480 frames out of the 500. But here we have edges that are only 150 frames. You won't have an edge if there are two. These guys are only close to each other for 2 frames because those are pruned already. So hopefully these frames are like, yeah, all right. Sometimes they come by, but who cares? These guys are neighbors. And again, it's different than the grooming clustering. This is a hair as it goes through these 500 frames. And it's trying to figure out how things move together. And we talked about how they did that last time. All right. So now, let's talk about selection of guide hairs. And I believe that's where we stopped. I think. If not, who cares? All right. So now you have this. Remember, oh, and there's one other thing I forgot to tell you, is that there's 100 or 300 million or 303 million nodes in this graph that they do a little trick on. They say, this graph is really big and it's a pain in the butt. I can reduce its size by 30, about. Because I, at this point, am just trying to cluster the hairs that move similarly to one another together. And so I skipped over this really quickly last time, and I apologize for that. Think about that. Let's say that this guy is this guy. I'm making this up, so this may not work. Well, yeah, sure it will. And I've actually got an edge between them because they're near each other. And there's an edge over here. This guy shares an edge. Let's put in another edge here like that. No, let's do that. So because these two nodes are on the same hair, we're going to squish them. And by doing that, we're going to reduce this. First of all, we don't no longer need the edge between them. They become one node. So that node goes there. But these guys share this edge to this particle. Both of these guys are really close to that particle, which might be, that particle there. So what we're going to do is take these two edges and combine them, and we're going to have an edge between the comboed particles and this other particle, which isn't part of the hair. And we're going to take the counts and the weights. There's a number of times they came close to each other, and there's also a weight that we talked about how strong the connection is between these two guys. And we're going to sum those guys together. We're just going to sum them. So this count is equal to the times this guy came together and the number of times this guy came together. And you think, oh, are they just summing, or are they averaging, or what are they doing? No, they're summing, which surprised me. But then I thought, wait a sec. The way they're building this thing up is to make sure that strong connections stay strong and weak connections stay weak. They want to actually emphasize that this particle and this particle are seeing this particle a lot. So when the clustering algorithm works on this reduced graph, they're going to see a boosted thing there. Now, edges that aren't collapsed, like hopefully the edges between particles and stuff, won't get that boost. And so this says these two particles see this guy, and we want to make that bigger. So we're going to just sum the counts associated, and it gets stronger. At the end of it, we take all these particles that are on one hair, and they all get crushed down like this into one node in our graph. So now we have a graph that each node represents a hair. So now we're down to 100,000 elements. And the edges have been lifted. They've been the edges now emphasize the closeness, the proximity even more. I thought that was cool. It was kind of cool when I finally figured it out. All right, so now, step 2, selection of guide hairs. So now, assume these are just nodes which represent guide hairs, not particles on the hair. Once we've clustered them like this, once I've said that these guys all seem to move really similarly. They're close to each other, and they're moving a lot like each other. How do we figure out the hair that we want to use to guide the rest? Because we only want one guide hair out of these. Remember, this can have a lot of hairs in it. You can have 50 or 100 or however many hairs. It's the number of hairs divided by the number of clusters, right? And that's how many hairs, hopefully, you'll have. Clustering algorithms can often build huge clusters and small clusters, but you can also convince the clustering algorithm to continue to work on it until it builds equally sized clusters. They talk about that later on where they really care about it. They don't care about it as much at this phase. We'll come to it when we come to collision resolution. All right. So what do? Well, basically what we're looking for, and let's write down this equation and we'll go over the details. There's a function, f of g, and we'll describe everything here. Sum I is an element of G. G is a cluster, and we'll get to that. And then sum J is an element of the neighborhood of I in G. Sorry. And this is U sub I. Okay, so although there are many choices on guide hair selection, given the large size of graph nodes, we prefer a method that that balances the computation cost and the quality of the resulting skinning model. Never before we propose a hair selection algorithm that maximizes the following energy function. Right, now remember, the U here is the how similarly are these particles moving. We know that they're close together. You guys moving in lockstep? Are you moving? Are they behaving similarly throughout the entire simulation? And I is the index of a hair, and J is the index of a hair. G is the set of selected guide hairs. So we're only working on this one group of guide hairs. We're trying to find this maximal energy function. I denotes a guide hair, a normal hair, and J denotes a guide hair in its neighborhood. So we're still within this cluster, right? Because that's what that says. We then select a guide hair to maximize the similarity between every normal hair and the guide hairs in its neighborhood of algorithm. So you think about it and you go, wait, what? Oh, they're trying to find that one eye that makes this thing, this part of it over here, the biggest. So we're looking for all the combinations. There's, you know, I's and J's and everything, but there is one hair in there that has this part of it the biggest. We have to find that. Unfortunately, it's a trick. It's a bit of a thing. So the first, this isn't the hard part of the algorithm, but it's not that. We select an edge in the node that has the maximum summation of edge weights. So we look for that guy. Note that these nodes cannot guarantee maximum energy value because two selected nodes may connect with each other. So whatever. Then we sequentially operate on every single group and fix the other groups. So we're going to be doing this. We pick a hair here, because remember there are connections going across this. And we pick a hair here, and we look to see if that maximizes this. So we just randomly pick one. If it doesn't, we'll try a different one here and leave all the other selected hairs the same. So we then sequentially operate on every single group and fix the other groups. So we don't change anything else. And we start messing around with this and saying, you know, is there a hair here, given the connections between the groups, that actually works better in that overall function? We select the node that leads to the maximum energy value as the guide hair and move on to the next group. So we do one group, then the next group, and the next group, and then we do it all over again. We keep doing this over and over again, where we have basically chosen what looked to be the best, and then we confirm that it's the best given the neighborhoods of these things. And they say, the cool thing is, because every time we choose a different hair, it's actually making this function bigger. It converges, and it actually converges relatively quickly. So this wasn't a slow part of the algorithm. Finding the hairs in each one of these groups that work the best in terms of guiding the rest of them, it actually works. And they have a graph in the paper where they say if you just randomly choose hairs, you know, just randomly pick one hair from each one of these things, you get crappy error. If you spend the time to figure out the optimal hair, then you can get some pretty low error. And then there's this red graph in the thing that's, if you use this algorithm, which runs really fast, it's not bad. There is a little bit more error, but we don't care. It looks good. Okay, so sort of skimmed over that, and I'll leave this. If you're interested in the details, of course, there's always the paper, but hopefully you get the idea. At the end of all this, what do we have? We have clusters of hairs, a whole bunch of hairs in here that have connections between them, and a whole bunch of hairs in here, and a whole bunch of hairs in here, and we have these connections between these guys, and it goes all over the place. And at the end of it all, we have one guide hair here, one guide hair here, one guide hair here, and one guide hair here. So we basically just partitioned our entire head of hair into groups that move similarly, guide hairs that control the groups, and we also know how these guys are talking to each other. All right. So now, we're doing well. We're doing well. This will be fun. Let's go back to the very beginning. Talk about how hairs move. So S sub I, that is a single hair, position in world space, the transform of the head times this G element Ci. I'll explain what that is. Wij Bg S star. All right. When interpolating the state of a hair, the normal hair particle I, or the state of the normal hair particle I, we consider a set of Ci guide particles that affect I, and update this thing based on this. So remember, now we have guide hairs. Now we're backing off. We're going back to particles. We're going back to this fact. We kind of scrunched everything down from particles into hairs. Now that we've got the hairs, great. And if this guy is a guide hair, it got chosen as a guide hair, we're going to change the color of the hair. We're also going to change the color of these particles, because these guys are guide particles. Right? Remember, that initial big graph that we built with all the connections between all the particles still exists. We did a scrunch down of it to get the guide hairs, and then we're done with that. We're going to go back to the original one where we have all the connections between all the particles. So if I go back to, let's go to this. If I go back to that original graph, and I have a particle in here, and I have other hair particles that are connected to it, I'm interested in this particle S sub I and the guide particles that have edges between them. So some of these particles have been boosted up to guide particles, right? So these guys, not all of them have, but some of them have been changed to guide particles, and they have a G associated with it. These guys are guide hairs. So S sub I is now going to be a weighted combination of how those two guys move. And it's that simple. Remember, we take, think about what this equation says. S sub I star with a bar over it means that it's at the rest state of the hair, this hair particle, one particle like that guy right there. State of the group. B sub G is how each one of the guide particles is moving. And so there's a different B sub G associated with this guide particle and a different B sub G associated with this guide particle. So we're basically saying, I know how this red dot here moves, and it's close to this guy. B sub G that tells me how to move this red dot from its rest state to its current state. I'm going to use that same transform to move my normal hair particle. But I'm going to weight it because I probably have a graph of multiple guide particles that are influencing how my normal particles are working. So you're basically looking for all the particles that have edges connected to the particle we're working on that are guide particles. We're going to associate a weight. There will be a Wij here, and a Wig here, and those are different G's. I write G0, G0, and G1, G1 here. All right. And then, once you do this, notice this is all in local space because it's got the bar over there. This will compute the location of the normal hair particle, the blue particle, in local space, and then the T will move it so that it sits on top of the head. Easy. Except, what the hell are those? How do we compute that? That's where the machine learning stuff comes in. Or, well, in this case, it's very minimal machine learning. But think about it. This is where we want to start thinking about actual machine learning. So how do you do this? Well, remember, we have 500 frames of simulation, right? We have training data, and we can watch the training data. We can go through and say, at frame 10, I know where everything is. I know where all my particles are. I even know where this guy is because I've simulated, right? I have a full-on simulation of my hair. So I know this, and I know all these guys, and I know that. The only thing I don't know are these. And I have a whole bunch of frames where that happens. So you can see that the problem is actually kind of simple, right? You're looking for weights that over all the frames that where these edges exist, right? And you're only doing this. That's a good question. Do you do it only when they're close? I think you probably do it for all the frames. Actually, I take it back. Is it all the frames? Yes, 1 through F. So you go through and look at all the frames in the hair simulation. Doesn't matter how close they are anymore. They are paired together. And you say, is there a W, I, and G, or a W that associated with each one of these little edges that makes this work the best for all the frames? Well, the answer is yes, but it's never going to be perfect, but it's going to be close enough, right? Because we've done some stuff. We've assumed that these guys are all moving together. We built this graph so that these guys are moving very similarly. So what we're looking for is a weighting scheme that sort of minimizes the error that's coming along here. We're looking for this thing. Then, this is the cool bit. It's fast, right? Think about what we're doing. First of all, the number of guide particles, we've shrunk down. The number of guide particles we got are, 100,000 hairs to 200. So the maximum that this sum will be is 200. Well, no, it's 200 times the number of particles per hair. So the maximum this would be 6,000. But it's not going to be that. That's going to be huge. Sum over the nearby particles to this guy, and this is not a huge sum. This is a small matrix. It's easy to compute. This is a multiply. So doing this kind of stuff, this is what graphics cards do. You can fly through this kind of stuff. Even though we have 100,000 times 30 minus 2, close to 3 million hair particles, evaluating this is actually very rapid. And we can do it all in parallel. Zoom.
Are the weights convex?
Yes. The weight. Ron asks a great question. Are the weights permitted in even? No. The weights have to be from 0 to 1. And they also have to sum up to 1. So that means that you're not going to have this you're not going to solve for something where it goes zing. You're going to stay within this box that's defined by the guide particles.
Presumably, different particles will have different numbers of neighboring guides.
Exactly.
It's got to get normalized.
It has to be normalized. And the nice thing about this is, speaking of that, you can solve for this. Again, this is all done in post-process. We're training it based on this. Each one of these solves is separate. So one particle's weights versus the next particle's weights, you can just do it all by yourself.
Question, and I confess I still haven't read the paper.
No worries.
So we are doing this step to figure out the weights, and it does have the benefit of getting the normalization. But when we were just moments ago doing all sorts of graph construction and weighting edges and then simplifying the graph and stuff like that, and it seems like we've done some of this work before. I wonder if there's like some graph algorithm that you could do and that same information might be encoded somewhere. I don't know,
I don't know either, actually. No, I don't know.
I was kind of wondering the same because we had some interesting strength information from the last bit. So like if a hair moves out of a certain distance, does it sort of let go of it? And the weight goes down and eventually it disappears from that network, or?
Well, we kind of threw all that particle information away when we collapse down the graph.
Exactly. Well, for that, well, we didn't throw it away. We did that to find the guide hairs, but we still have all that particle-to-particle information. We keep both graphs because that other graph is, this node-to-node graph or particle-to-particle graph is going to come up again when we do the collisions. Maybe.
Is the guide hair selection thing just really that key, or is it just paper filler? Like, if you just picked by like saying let's find a good let's do Voronoi tessellation on the head surface and just pick the centers of those, and whatever's there, we'll just pick it.
Actually,
Yeah, how much
think,
can this cover, right?
I think there's something neat here, though, in that, like, that would be actually pretty close. But you could imagine some more exotic scenario where actually using nearby hairs turns out to be misleading, like something about your simulation. You know, I think what is neat about this is,
right?
Exactly.
Yeah,
so I think what's neat about it is it's like, well, I'm not going to make those kinds of assumptions. I'm just going to see what does the simulation actually do.
And remember that U that we have, the U that's actually computed to determine the difference between these things, is how those hairs are moving in lockstep with each other. And I think that's the thing that, and that's kind of important for this to actually come up with reasonable results. These guys have to be part of the group that moves together, I think. Yeah, I mean, it's a great question. Quite frankly, at the end of the paper, they do say the most important thing of all, pull this out, is the most important parameter of our reduced model, so there it is the number of guide hairs. Not the selection of the guide hairs or anything, but how many guide hairs you have controls a lot of how good this thing looks.
It does seem like it would help with things like natural part line areas that are simulating in different directions, or like curly hair clumping.
Yeah, agreed. Especially the curly hair stuff. Remember, you've got a single curly hair that's controlling a clump of curly hairs. You want to make sure that those guys get the influence of the neighboring curly hairs is resolved correctly, right? All right. So, how do they solve this? There's some details. I want to get to the collision stuff, so I'm going to skip over it. But you basically have a sort of constrained optimization. They use we simply solve the linear constrained least squares problem using a quadratic programming solver implemented using QL. So I don't know what QL is. So they're doing quadratic programming because you're basically looking for the weights that minimize an energy function that I'm going to skip over as well. And that's within 0, 1. It is a linear problem. Well, all right, I'm going to write it down. I'm going to write it down because you just asked. And I always look for an excuse to write down math because it always clears things up. So they are minimizing. I mean, we're going to yeah. Let's see. Minimize the WIs, right? For all the frames, F equals 1 to F. And, yeah, that's F. And then we're taking the 2 norm of this, sum of G sub the element of CI, WI G E G. I'm basically writing this down. S per star S supply per square, and it's kind of exactly what you'd expect, right? So this is the sum applies to this. So they're basically saying let's compute that and compare it with the actual location of the thing that we know where it is because of the simulation. Sum it up over all these guys. We know this because we know that the nodes involved in moving this guy because we have our original big graph that we built, and we do it for all the frames. So it is a linear least squares problem, right? It really is. You're just looking at that. Yeah, and you can solve this pretty easily. This is not a scary thing. The one scary thing, well, I'm not scary, but the one W has to be greater than 0, less than 1, less than 1, and the sums of all the W's equal. Right. Okay. All right, we're going to resist. Now we're almost there, actually. Now all we have to do is simulate the guide hairs. Cool. Like I said, skipping over that, they use the Stanford-based thing with friction and springs and stuff. Simulate the guide hairs. We can compute the motion of all the normal hairs using the equation that I just wrote. Awesome, except for collisions. So now what we want to do is resolve the collisions. And I thought it was kind of interesting. So, first of all, so I'm just making sure I know where I'm at. Collision-based, okay. Now we now correct all the hair particles to resolve collisions. Given a limited time budget and a large number of hair particles, it's necessary to keep the collision resolution as light as possible. Therefore, the natural choice is to correct hair particle positions using position-based dynamics. Yay, we use position-based dynamics, yay, and that didn't work. Our first attempt to follow position-based dynamics and project hair particles using collision constraints with a few Gauss-Seidel iterations. This takes forever. With this many things. The correction is independent at each time step, disregarding the temporal coherence of the hair particles. It leads to rather pronounced flickering effects, and it's not all that fast. Because some corrected hairs can move back and forth with niggling. So, instead, what we're going to do is have this energy framework. We're going to introduce, and if I could tell the authors to do one thing, is to stop using the same letters for different things. Because they then say G. And remember, they've been using G's for guides all over the place. But this is a different G. This is an energy cost function. It is equal to, what the hell is this? So we're going to write this down again because square, this is the 2 norm, and then I'm going to do carriage return here. This is still all under, but this is a different sum. Sum, oops, k h squared over 2. Sum of I, j. Oh my god, what the hell is this? It's it's illustrative to sort of figure out what they're doing. J minus dr. How crazy is this? Pi minus pj. This is easy. The distance between pi. Now we're going to normalize some things here. Pj. Okay. Well, first of all, the pi's are the positions. Notice we have s's here. And S is position in tangent. We're worried about collisions. We just want to move these things out of collision. So all we're doing is worrying about the P part of that. That's a P and a T in there. And so we're just taking out the P. PIs are where the hairs are after you simulated the guides and moved all the normal hairs with the equation I just wrote. Easy. Pi prime is the position of that part of hair particle that is not in collision. This is the connected particle position that we need to solve, that we're solving for. We want to make this thing be out of collision. All right? M is the mass of the particle, that guy. Probably it's a constant for all these guys, but you do need a mass in here. H is the simulation time stuff. So how fast are we moving? dr, and here it is the collision distance threshold as used in our penalty-based collision model. Now we're starting to see. Okay. L indicates this. Where's L? Oh, this is not a C. That's an L. It's just very small. It's a dark green. That's an L. L indicates the set of particle pairs whose distance is less than dr. Basically, you've got hairs, or hair particles that have come too close to each other, right? We want to make sure that this hair maintains volume. Hair simulation plus our interpolation, we've scrunched some hairs way too close to each other. So I'm going to fluff them out. So dr, or L indicates the set of particles whose distance is less than dr. And now think about that. There's
NK?
NK, we're getting there. The second term of G penalizes the violation of the collision constraints. All right, we'll get that. While the first term penalizes the deviation of the corrected position from the interpolated and temporally consistent positions, or coherent positions. Lastly, K is the parameter to balance both terms, also used as a stiffness parameter in the particle position-based dynamics framework. So wait, what? Oh, look at this. So first of all, this is the energy of our system, right? So this got to, due to all the simulation. This is the place where we'd like the particle to be outside of collision. So we've noticed that this particle has gotten too close to things, right? And these particles can, and quite frankly, we can to resolve particle to geometry collision. We sort of just skimmed right over that. This is all hair to hair, particle to particle collision in here. So we want to make sure PI that we compute to resolve the fact that this particle got too close to other particles is still as close as possible to what we think it should go to. So if this gets bigger, if this gets longer, if those two particles, if we start moving that PI prime away from where we thought we wanted it to go, this is going to get bigger and bigger and bigger and make this energy term get bigger and bigger. And that would be bad. Bad. Notice we're also doing this for all P's. So this is, the P is the particles that are in collision. And so this is a state of the system. It isn't a single particle at this time. It's all particles that we're looking at. Then we're also summing over all the particles that are close, that cause them to be put into P, right? So we're going through this thing and looking at all the edges close to that. Not all particles are going to be too close to each other. This is an overall big set. Some of the particles won't even be there, but some of them are. And so think about this. You're looking at the change in particle I, where we're going to move it to get it out of the way. We also have to look at where we're moving particle J. And we're going to look at how far those two are apart. And then, first of all, we're taking we're basically taking these two particles that have gotten too close to each other and creating a vector, right? There's particle I, and that's particle J. And we're subtracting the two. All right, we're making that just a distance vector, and then we're multiplying it by how far we want them to be. So dr might be that distance, right? But these two particles have gotten too close. Take this and basically make that. We want these guys to be that far away. Now, we're basically taking this, and you can move these guys however you want, but we want to make sure the distance between these two guys is that. Here's Pi prime, and I have Pj prime, and that's the vector between those two. That's that. This is that line, and we're basically comparing the two vectors. We're saying, are you guys farther away from each other? And then you look at the length between those two things. And that is how they're making sure that the particles are farther away than they need to be.
So you could very easily get edge collisions here, right? Hairs are still going through each other completely.
Correct. None that never shows up in here. Yeah, absolutely. Ron brings up a good point. Hairs going through each other where edges go to the other, we don't care about that. In fact, I think that's due to they're kind of relying on the time step. If you have 30 particles edge to edge, fingers crossed, that when you do a hair-to-hair collision that goes like this, some of those particles are going to get close to each other, and you're going to hope that it pushes the car. But it won't. This is not a guarantee. Absolutely. You could have. This is not going to prevent all hair-to-hair collisions. All right. Now, think about this. This is interesting, and it's cool, but it's a big system of equations, right? Because you can imagine in one simulation, you're going to have a lot of particles that are getting too close to each other. Thing up where you maximize, well, you've got this energy value that says how close are these guys squishing together overall? We want to make this as small as possible, reduce the number of squishes to almost zero. We'd actually like this to go equals 0. All right. So in constrained or position-based dynamics, it's exactly what we're going to do. In fact, what we actually do is and I'm writing this stuff. This should be all pretty easily. This is just length of vectors and stuff here. This is the gradient. So what we're going to do is look at, is there a way for me to change the positions of the particles such that the system goes is basically finds a minimum. This is not setting it to 0. That would be optimal. But this is basically looking to say change the particles so that this system actually finds this sort of minimum or maximum, but in this case minimum. So this is remember the gradient is how this thing changes with respect to the change in P. And this actually turns out to be a cool, now we're running out of time. This, if you go back to old chalk talks where we talked about position-based dynamics, this is a constraint, a way of solving, it's more of a way of solving a constraint in position-based dynamics. And position-based dynamics has a fairly decent way of dealing with constraints like that, where they're basically going to move one particle, then move into the next particle to help with this, move the next particle, help with this, move to the next particle, and help with this. These guys have taken that and sort of, they've done some cool stuff. Form-based dynamics works with a sort of Jacobian iteration so that they can maximize parallelism in solving this problem. And we are out of time, and we're not going to come back to this paper. The section where they do this is a little bit complicated, but it is understandable. At the end of it all, I'll erase this because we're done with that. At the end of it all, we've taken the positions. We've got hairs, guide hairs that are moving, and all the rest of the hairs, right? The hairs, we've got guide hairs that are moving. We use the guide hairs to drive the positions of all the rest of the hairs. And then we make sure there's this one step where we take the positions pi of all the hairs and move them to pi prime to basically help out with the collision. And we go on to the next step and the next step, and it actually runs pretty fast. They do a couple of things. They formulate the update of this as a Jacobian iteration, which I'll talk about some other time because it's kind of cool. A lot of this in parallel. They also cluster. They do another cluster to make sure that you're only doing particle to particle that come close to each other. I'm skipping over that too. And then finally, they do a neat thing where this matrix that they build, they have a way of updating it without rebuilding it each time, which I thought was super cool. But we're done. I highly encourage you, after watching all this crap, to go back and look at the videos. At the end of the video, they have the researcher being watched by a web camera. It's tracking the position of his head, and he is moving his head, and you see a character with the hair reacting in that 30 millisecond time frame. And they spent a lot of time trying to stay within 30 milliseconds, and they achieved it. To these guys, it's good. 100,000 hairs, right? So that's pretty cool. Whew. All right. I swear, this is a SIGGRAPH paper, right? This is a paper from 2014. You get 23 minutes to talk about a SIGGRAPH paper. We couldn't even do this sucker in 2 hours. And right there. All right. That's why we.
Question and a couple of comments as well. So one is, when the optimization equation was written, was there anything to restrict the guide hairs that got associated with hairs around it? So if I have very similar motion that is running in the opposite or on the opposite face or on the other side of the head.
Okay.
And what if some particles over here get associated to guide hairs on the other side of the head?
Oh, well, that should never ever happen, though, right? That's what the clustering is doing, right?
I think they're thresholding like, oh, it has to stay together in the neighborhood for a really long period of time.
Yeah.
And move in a similar direction.
And move in a similar direction. You should never have a hair
Well,
particles.
if for some reason the hairs on the back of your head and the front of your head moved exactly the same way, then it's okay.
No. But there's still the distance,
Oh, the
right?
distance is also.
Yeah, when they're building that initial graph, the only time they build an edge between a particle is if those particles become close enough to trigger an edge creation. So it is never going to influence this part of the head, because those particles will never, unless you're in a tornado or something like that. Don't train it with tornado. They do say that this is a trained simulation, right? And so if you train it with motion and then try to simulate something that goes beyond the bounds of that motion, it's not going to work all that good. It is not an extrapolator, it's an interpolator. So you want to stay within the bounds of how your hair moves. Right? Okay, so idea, right? The linear combination of guide hairs, right? Why does it have to be linear? We've been doing a lot of machine learning stuff. Whenever you see linear combination of stuff, you could also start to think, oh, hold on. We have this blob of particles that we know are traveling together. Why not throw it at a little forward, little machine learning thing that can be nonlinear? We've seen some really cool success for that. And this is all training data, right? So we can actually spend some time. You can have a little machine learning thing per particle. There would be a lot of machine learning going on in this. But all of a sudden, you might even be able to do collision detection using, which I'm going to hold off for conversation play, because I have an idea on that too.
And,
right.
Also,
yeah, one more.
I believe the equation forms up to be a linear least squares, but it's a constrained linear least squares. So placing upper bounds, lower bounds, as well as the weights summing up to 1 is far easier to program using the quadratic programming solver.
Which they do, right?
Yeah.
I mean, that's why you can't just use any least squares solver.
No. But yeah, it has to be. That constraint makes it trickier. It's doable though. That's what I was trying to communicate, right?
Well, I'm guessing quadratic programmer implementations also internally use least square solvers, but placing those constraints, I'm not entirely sure how the method works internally.
But again, one of the cool things, machine learning, you have those activation functions, those tan H's. Weights at the end to be between 0 and 1 automatically. It happens on that. I don't know. Well, just a thought. Guys, see you later. No Chalk Talk next week. They're going. No Chalk Talk next week because it's July 4th and no. But then after that,
I'll do it.
Nafis is going to do a practice session of a SIGGRAPH talk that he's got.